So this is a Newton's second law problem, but I ask it now because it's relevant to the topic we're about to start. Let's just really quickly, without going through all the Newton's second law steps, let's just think about this object, right? The piano is attached to the pulley, so that is one object, and look at the forces on it. There are two ropes pulling it upwards, right? There are two ropes pulling it upwards, and there's gravitational force pulling it downwards. So there's a tension in that direction, a tension in that direction, and the gravitational force in that direction. Doesn't matter that the rope's attached, it's still two ropes going upwards. And then you have to be pulling with the same tension, because the tension is, as long as it's a massless rope and they're massless, frictionless pulleys, which we're assuming everything's ideal, that you've got to be pulling with the force Ft in order to put the tension in the ropes at that point. Okay, so we've drawn a free body diagram. No, we haven't drawn a free body diagram, but we've indicated our forces in a force diagram. Choose our positive direction. I'm going to make up plus y and write F net equals ma for the piano in the y direction. There is no x direction. And therefore, we've got plus ft minus fg equals the mass of the piano times the acceleration. We want to be able to just move it. So an acceleration of 0 is all we need, or greater than 0, right? So it would be this is one of those things where on the border of, if we want to move it, it just means acceleration greater than 0. That means we can use an acceleration of 0 and say it's just got to be greater than that. So therefore you get 2ft equals fg, and therefore you get ft equals fg over 2. So we only have to pull with a force of half the weight of the piano. The piano has an approximate weight of 1,000 newtons, 250 pounds, about 1 to 4. 1,000 newtons, that was the number that was given in the problem. Then you only have to pull with 500 newtons. Why? Because you're using a pulley system. And the pulley system is a simple machine which allows you to reduce the force that you have to exert to move something. Just like, right, a simple machine would be a ramp, where you push something up a ramp in order to get it up a certain height. If you had to lift an object M up a certain height, you'd have to exert a force. If you had to lift it just simply from the ground to this height, you'd have to exert a force of mg. But if you're pushing it up the ramp, you're only exerting a force of mg sine theta. That's something that we've done, a number of times when solving problems. Right? These are called simple machines, that we exert forces. We create these machines to reduce the amount of force that we have to exert in order to lift something or to move something. You could get a more complicated pulley system, let's say like this one, and tell me now what is the force F that you would have to pull in order to lift this weight W. Well, just count the ropes, right? There's 1, 2, 3, 4 ropes. So you got 4 tensions going upward for one weight going downward. Fg, Ft, 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 Ft. So 4Ft equals Fg. That's what a pulley system does for you. So in this case, F would equal to Fg over 4. If it's an ideal system, right? If the rope the rope and pulleys themselves aren't too massive, or friction or stuff like that. Anyway, so you can reduce the amount of force that you need to exert to lift a body by creating all kinds of simple machines. So we can look at this one, or we can look at this one, but let's just look at this one and say, okay, what we're moving on to is a concept called work and energy, and we'll define that in a second. But before, I want to connect this to that. Sorry, I'm stumbling over my words. We're going to talk about what are called conserved quantities. Quantities that are conserved. The concept of conservation in science is essential. If we didn't have the concept of conservation, we really couldn't do science. And what I mean by that is the fact that, for example, mass is a conserved quantity. If you take an automobile and it has a certain mass, it's got a mass of 1,000 kilograms, and you take a tire off that automobile, The automobile's mass is going to be smaller, right? But does the mass disappear? Is it gone? No, of course not. You took a tire off and you put it somewhere else, so the total mass is still conserved. This is the idea of a conserved quantity. Force is clearly not a conserved quantity. Force is not a conserved quantity because you can see through these simple machines that I can reduce the amount of force that I have to exert to lift objects by creating a simple machine. But there is something else that changes. So instead of me simply lifting this piano, I could just do that, but I could just do that, and how much force would I have to exert? The force that I would have to exert, the tension in the rope, is going to be equal to Fg because there's only one rope, right? So instead of doing one rope, I can do two ropes, so I've reduced the force, but what else is different? Something else has to be different. And we'll talk about why it has to be different in a second. What else is different between this situation of a single rope and this situation of two ropes? Or even the situation with four ropes. What is different? Pause and think about that for a second. But I'll tell you what is different is the amount of rope that you have to pull in order to move it up a certain distance. So let's say that I'm moving the piano up a height h from the floor. How much rope did I have to pull? Because I had to move this rope up a height h and this rope up a height h, then I had to pull 2h worth of rope, right? There's going to be 2h worth of rope that I had to pull. And so therefore, right, as compared to this one, if I lift this piano up, and sorry, it's a terrible picture, but if I lift this piano up a height h, then I simply have to pull this rope down a distance h in order to lift the piano up a height h. But I'm exerting the full force of the weight. Again, here, I'm exerting half the force of the weight, but I'm pulling twice the amount of rope. And here you can hopefully guess that if I'm pulling 1/4 of the weight, then I am pulling 4 times the amount of rope. The length of rope, L, is equal to 4h, 4 times the height at which I would lift the object up, if L is the... Okay, so as I reduce the force, I must increase the distance that I pull it. And that's the same thing with this mass on the ramp, right? If I lift the object straight up, I lift it a distance h. But if I push it along a ramp and I reduce the force by a factor of sine theta, I actually increase the height by a factor of sine theta. Same thing as I reduce the force by a factor of 2, I increase the length by a factor of 2. If I decrease the force by a factor of sine theta, then I've increased the distance. The distance along the plane is going to be h over sine theta, while the force is equal to mg times sine theta. And then this distance here is going to be h over sine theta. You can do the math yourself. But every time we reduce the force by a factor, we must increase the distance by the same factor. That's what I'm getting at. And this gets us to the concept of work, which I'll get to in a second.